Hey everyone, this is Sai, one of your TAs for STA 371G this fall, and I, along with Vasco, who's the other TA for the course, will be making short videos of the R help sessions that we conduct on Fridays as a part of the course. All these videos will be uploaded onto YouTube in this very same channel that you're viewing from, and the link to these videos will be posted on your Canvas page. This is the second video for the semester, and we highly recommend that you all attend the art help sessions on Fridays. And if you can't, then these videos should give you an overall summary of each session. And we really hope you find these informative. In the first video, Vasco talked about creating R Markdown files, saving them, and gave you some basic commands to work with in R, like addition and multiplication, reading a CSV file, viewing any data set on R, and calling certain columns from a data file. Well, today's session is going to be an extension of the first video. Today I'm going to be talking about creating an R project, which you would find helps you a great deal with keeping working directories intact so that you don't have to set your working directory every time you open an R Markdown file. I'm also be teaching you how to plot data to visually analyze relationship between variables and to calculate correlation coefficient and the statistics behind the correlation metric, adding a new data point to an existing data set, and linear regression using the LM statement and the statistics behind simple linear regression. Having set the agenda, let me quickly move to R. I hope everyone has RStudio installed on your systems by now. And I'm going to start the session now. So the first thing that wanted to talk to you about is to create an art project. Um, a lot of people who've been coming to the office hours have been complaining that they've been having issues setting working directory. And there's a really simple solution to get rid of that issue, which is to create an R project file. It's really simple. All you have to do is just be a little more organized. We recommend that you guys create a folder for this particular course, name it as STA371G or whatever it is, and store it in a convenient location for everyone. Um, so uh, as you can see in my system, I've kept it at C, my name, UT Austin, fall, and 371G. And this folder is where I'm going to be creating the art project file. You can actually see that I've already created it, but I'm going to show you how to do it again. And essentially, what I'm trying to do is I'm trying to get in all the data set that I need for the rest of this course, or even all, like um, all these RMD files and everything onto the same folder where I create this project file so that I can just open this project file and I'll have all my RMDs listed and all the data set listed and the working directory already set. So with that being said, I'll move to RStudio. So if what all you need to do is create one of those folders that I talked to you about, and then you just go over here and click New Project. It asks me to save my existing project. I'll do that. And if you've already created that folder, all you need to do is choose an existing directory and browse to that particular directory that you've created the folder. So just go to that folder and click open and create project. That should create a project file, just like the one that you see on your screen right here, our project file. So I'm not going to be doing this now because I've already created the R project. I'm going to be working with that. So once you create the R project, you should see this very same screen, but without the RMD file, because again, you need to create an RMD file and add to that. but you will essentially see a blank screen over here, and everything would be blank except for the fact that there will be the folder name or whatever the project name that you've created. You should be able to see it over here. Since Vasco already talked about how to create an RMD file, I'll not really get to the specifics of it, but I'll just tell you how to create an R Markdown file. You just go click over here, R Markdown, and then name it whatever you want. Author, you can be yourself, and then save it as a HTML. Okay, that should create a new R Markdown. This is what the R Markdown template looks like. And any chunk of code that you need to add to it, all you need to do is go to Insert and click R. That would create this template for you so that you don't have to, like type in this, rather this every time you want to create a script. You don't have to do it. So um, you could just go to the Insert option and click on R from there. I'll close this real quick, and I'm going to be working with uh, the existing RMD file that I have with me. So, um, the first command that you see on your screen, the one that the cursor is highlighting right here. So it's the RM command, which is used to remove objects from a specified environment. So as you can see from my screen, I have a lot of data and values existing in my global environment. And for beginning the session, I'd like to clear them all out so that I work with a fresh environment. And the way I can uh, run a chunk of code line by line is to just click on the end of the line of code and press Control Enter in the case of Windows or Command Enter in the case of Mac. So if I do that, it's going to run just that one line of code. And as you can see, the RM command has emptied my global environment. Um, well, now that we've created the project file, what you need to do is if you just go to your course Canvas page, I'll do that real quick. So whatever data that you're going to need for your assignments or even for these help sessions, they're going to be available on your Canvas page for the course. So just go to the dashboard. Um, okay, my internet is really bad. I'll just wait for it. But essentially, you just go to the data file that's there on your Canvas page, whatever data you want to download, and put it in that very same folder um, that you've created the R project file in. And by doing that, you should be able to see the CSV file that you've downloaded here in the files over here. So by doing that, you've already set the working directory to this particular folder, and you don't have to essentially type in this line of code every time you want to operate R. So I'll just skip that. I've added that as a comment. Now I'm going to be reading in the data file. So this is a cyclist fatality data. I'm going to be showing you what the data looks like in just a minute. But I'm just naming it as file name so that I don't want to type in cyclids fatalities.csv every time I want to mention it. So I'm just renaming it to file name by creating an object. So you can see that file name is an object that's been created, and it's appearing on a global environment now. So what I'm doing now is I'm reading in that file name, I'm reading in the object using the read.csv command, which is what we use to import in CSV files into the global environment in R. So again, I'm naming this a data file as data.raw, and now I want to view the data and look what it looks like. So this is data for different years, and this is the mean age of cyclist fatalities for those particular years. What you can see is quickly what you need to identify with any data set is you need to establish which one is the dependent variable, which is the y variable that you want to run a regression for, and which one is the X variable. And I'll be talking about that when we get to the LM statement. But that essentially is the data set. And now what I want to do is I want to plot the data and see what it looks like. So plot is the command that you need to use. Since I've stored the object as data.raw, that's what I've named my object as, I'm going to be calling plot parenthesis data.raw. That should give me a plot. So as you can see from my screen, the main advantage of using an R Markdown file again is that it it creates plots in that same window. Uh, for those of you who have been using R scripts till now, you must be familiar with the fact that if you type something over here in an R script, and if it's a plot, then the plot shows up somewhere over here. So under plots, it shows up, and then you can export it as a JPEG or as a PDF or something like that. But essentially, what we're trying to do by using an RMD file is for you guys to just submit one RMD file, and we can run the whole chunk and create some sort of a report without having to look at different JPEG images separately for each one of your questions. So that's what the plot looks like. It's just a simple plot of the X variable, which is year, against the Y variable, which is the mean age of cyclist fatalities. Um, so would you call this relationship linear? Uh, Most of us would say that this is some sort of a linear positive relationship, but a question of whether it's a strong relationship or not, I think that's open to interpretation. Some people may still think this is loosely positive related. Some people think the relationship is much tighter. But I guess it also depends on how accurate you want your variables prediction to be. Like, for example, in certain fields, it could be the case that this is in fact a good linear relationship, whereas in certain other fields of study, this could really not be a great relationship to look at. So it also depends on how you view the data. Well, there is statistically a way of defining how strongly two variables are related to each other. It's called the correlation coefficient. Some of you may be familiar with it. It's also called the Pearson correlation coefficient, which is it's a number between -1 and 1, and it's calculated so as to represent the linear dependence of two variables with each other. So a linear dependence of +1, a correlation coefficient of +1 would indicate that the y variable is positively exactly linear with the x variable. -1 would imply that it's a negative perfect correlation, and a value of 0 would imply that there is no correlation between the x and the y variables. How do you call this in R? There's just a COR statement that you can use. Again, since I've stored my data as the object data.raw, I'm going to be typing in COR of data.raw, and that should give me the relationship between the x and the y variables. And as you can see from the screen, um, year is obviously exactly correlated with year because it's the same variable. So you see an index of 1. Again, age with age is 1. But you can see that year with age, it's 0.9642, and hence age with year is as well 0.9642. That's the easier way of doing it. Well, there is some statistics that's going behind this correlation coefficient. So the correlation coefficient is in fact defined as the sum of each of your individual xi's minus the mean of x times each of your individual yi's minus the mean of y. The whole thing divided by the total number of rows minus 1 times the standard deviation of x times the standard deviation of y. So this is the actual statistical definition of the correlation coefficient. Um, and we're going to be using a set of commands to get to the same R value that the core statement gave us. So I'll just be demonstrating that. First, I'm calculating the mean of x, which is nothing but the mean of the year variable, which is our x variable. Having done that, now I'll calculate y bar, which is the mean of the y variable. So round is another interesting command that you can use. So round is essentially a statement that enables rounding of numbers. All you need to do is you need to select the variable that you need to find the mean for. In my case, it's the mean age variable. So that would be my x. So round of x digits equal to 0 is what you're seeing. So that's basically the a set of arguments that go into the round command. So x in my case would be mean of data raw, mean age, and digits in my case would be 2. So you don't have to type in digits equal to 2 every time. It's enough if you just type in comma 2 and that would take care of it. So having done that, uh, it's already calculated. But remember that unless I type that out and ask for it to be displayed, R will not display it. So now I'm displaying X bar. You can see that the mean year from the data set, it's 2004. And Y bar, which is the mean age for cyclist fatality, that's 37.85. And you can see that it's rounded it to two places of decimals as I've specified here in the code. Having calculated these two, now I calculate the standard deviation for X, which is nothing but an SD statement, and the standard deviation of Y, which again is the SD statement. Having calculated these two, now I calculate the numerator and I call it sum top. So sum top is essentially this, and you can see that it's just simple algebra. You can just type in everything. So R is a glorified calculator. It does all of your multiplication, addition, division, all these simple commands very, very easily. Um, and I'm displaying the numerator, and now I'm going to be adding the denominator to it, which is nothing but the number of rows in the data set minus one times the standard deviation of x times the standard deviation of y. If I run this now and I display what the correlation coefficient is, it shows up the same number uh, that the core statement gave me, which is 0.96427 as well. All right, so again, this is essentially the statistics that goes behind the core statement, which is wanted to show you how it really works. Uh, this entire set of calculation is done by R when you just give this line of command. Next thing, I'm going to be talking about adding a new data point to an existing data set. This can be done very simply. All you need to do is create another uh, row. This can be done by naming it as something you want. So, for example, in my data set right now, I have data till 2010 and the corresponding mean age for each of these years. So, if I want to add another, say, data set for 2011, I can just add something like 2000. I can create a vector 2011 comma 5, and then all I need to do is use the rbind statement and add this object that I've created, which is the vector that I've created, to the raw data that I already have. So let me run that real quick. So what it's essentially doing is it's updating data raw with the new column and naming it as data raw again. So it's essentially sort of iterating the raw data table and naming it as the same thing. So the next time you view data raw, it should have an extra data point in it. I'll run this and now I'm going to view that data. As you can see here, we had data till 2010, but now we have that extra 1 point that you wanted for 2011. So this is a simple way of adding, any data point to an existing data set and just renaming it. Now I want to plot this new data. Sorry, I want to plot this data set with the added data and see what it looks like. You can clearly see that the data point that I've added over here for 2011 has skewed this entire plot that I already have. So this is what we call an outlier. It sometimes it's caused because of a wrong entry in a data set, or sometimes it's because of other third-party factors. But generally, outliers tend to affect the correlation of data. So you can see initially my correlation for x against y was something around 0.962. But now, because of this one data point, you can see that the correlation has gone down by a huge amount. And the new correlation for x against y is minus 0.13. So it's this data point that's causing a huge change in the correlation. So generally, you need to identify what the cause for the outlier is and try to fix it rather than just remove the outlier outright. But in our case, we're just going to remove this outlier. And this is how you remove any kind of data point from an existing data set. So we just delete a row. That's why we use minus n row of data raw. And then once you do this and view the data set again, you can see that it's removed the 2011 entry from the data set. Right. Now that I've talked about adding and deleting a data point from a data set, I'll be talking about linear models. So, um, before I talk about linear models, I'd like you to understand the statistics behind linear models. Well, linear models is essentially something like finding the best line that fits your data. So you must have studied line equations in high school. Uh, so a line would have the equation y equals mx plus b. We call this the slope-intercept form in algebra. But here in data analysis or in statistics, we write it a little differently. We write it as y equals b naught plus b1x. It's essentially the same thing, where b naught is your intercept and b1 is your slope for the x variable. So chapter 4.6 in your textbook defines your slope and your intercept as the intercept is defined as y mean minus b1 times x, and then your slope is also defined as the correlation coefficient r times the standard deviation of y divided by the standard deviation of x. So I'm just running these very simple formula because I've already run the standard deviation of x, the standard deviation of y, and the r value of the correlation coefficient. I already have these values stored in my environment. I'm going to be running these commands and getting the value for my slope and intercept. And again, I'm calling out these two variables. You can see that the slope value is 0.807 and the intercept value is somewhere um, at minus 1580. Well, is there a simpler way of doing this? It is the LM statement, and I'll be talking about it. But before that, there's this there's a little bit of a difference between the numbers on your textbook and the one that you find here in our example. It's because of a rounding off error, and I think the textbook has rounded it off to two places of decimals shorter than what we have. So it should really have been 0.97, whereas it shows 0.96 on your textbooks. So I'll just skip that real quickly and get to the physical significance of what the line equation is really about. So we got here that B1, the slope was 0.807, and B naught, the intercept, is minus 1580.76. Well, using that, now we can form the line equation. This would be the line equation. It's y hat, which is the estimate of y, equals the intercept plus the slope times the x variable. So what does this actually physically mean? So it means that for every year, that is for every 1 year, the the mean age increases about 10 months because for every 1 year of increase, 1 unit of increase in year, you can see that y hat goes up by the amount of the slope, so which is 0.81 years, which would be 10 months. The intercept does not really have physical significance in our case, but I can show you a case where the intercept has a lot of significance. You guys must be aware of the relationship between Fahrenheit and Celsius, for example. So Fahrenheit is defined as 32 plus 9 by 5 times Celsius. So in this case, 32 would be the intercept and 9 by 5 would be the slope for Celsius. Well, what is the graph for a Fahrenheit against the Celsius uh, conversion look like? It looks like this. So you can see from here that when the Celsius scale, the temperature is 0, you can see that the Fahrenheit temperature is in fact 32 degrees Fahrenheit, which means that uh, the y variable assumes the value of the intercept when the x variable is in fact 0. So in this case, it doesn't really make sense to say that the fatality mean age for the fatalities is minus 1580.77. It does not really mean anything, but it could be the case that in some other data set, uh, like this one, converting Celsius to a Fahrenheit scale, um, the intercept could actually physically mean something because 0 degrees Celsius is 32 degrees Fahrenheit. Now we're going to be talking about residuals. So residuals is defined as the difference between the expected value for your y variable against rather the difference between the expected value of your y variable against what your y variable's actual values are from the table. So it's just the difference between the fitted line against your raw data. So the expected values can be calculated by using the same slope and the intercept that you found out from the line equation. And so I'm just naming that as expected. It's nothing but data raw dollar year, which is my x variable, times the slope plus the intercept. So this command should give me a set of 13 different numbers for y values for which x values are already defined in the data table over here. So now that I have my expected values, all I'm going to be doing is to calculate the residuals. I'm going to be subtracting my expected values from the raw data that I have for my mean age. So this resid, if I try to view it, it's essentially set of 13 values, which are the differences between the expected values and the raw data. So all I need to do now is I need to plot the residuals against the x that I have. And by doing that, so as you guys know, most of in fact, 3 out of our 4 linear regression assumptions, which would be um, the linearity, the homoscedasticity, or the equivariance, and the independence criteria. All these 3 can really be talked about by looking at the residual plots. So just by looking at the residual plot here, I can say that to an extent, we find that there is an equal spread of residuals below and above the 0 mark over here. And I can say that it's fairly equally spread. So it could be the case that in some cases there may not be an equal spread. You can actually find some sort of pattern that's existing in the residual plot, in which case you can say that it's not equal variance, but in this case, it seems that it's equally variant. So that's what residual plots are for. Now I'm going to be talking about the R squared value, which is essentially um, how much percentage of variance in Y is explained by the X variable. So this is also calculated as the square of the correlation coefficient. And since it's the square of the correlation coefficient, I'm just typing in R squared because I already have R stored as an object. So the value for R square that you can see on your screen is 0.929, which essentially means that 93% of the variance of the data is in the model, which means that 93% of variation is in Y is explained by the X variable. There is an easier way of doing this and getting all these summaries that you want. So it's called the LM statement. It's a linear model statement that we're going to be using a lot in this course. So the LM statement is generally used for fitting linear models. It can be used to carry out regression, um, analysis of variance, and analysis of covariance. But in our case, we'll be generally using it for simple linear regression and multiple linear regression. So these are the arguments that go into the LM function. You can see that there is a formula. The formula generally in a simple linear regression would be y against x, or in a multiple linear regression, it would be y against a series of x, which can be connected by plus signs. So it's like y against x1 plus x2 plus x3, and so on. Apart from that, you have to specify which data set you want to carry out the linear regression from. And there are some other arguments that go into the LM function, most of which we will not be using in this course. But the definition for each of these arguments are given over here in the R help page. All you need to do is, if you have any doubt regarding what arguments go into any command, all you need to do is type in question mark and the name of the command, run it, and it should show up the throw up the R help page that has the usage for that command. Now, I'm using this LM statement to run a simple linear regression of my mean age, which is my y variable, against the year, which is the x variable. There are two ways of writing this linear model command. The first is the way that you see on your screen. What's been done here is you're specifying already here that you're taking the data from data.raw, and then the dollar sign indicates which column you want to search in your raw data. So I want to search up the column Y, the Y against the X, so it's mean age against the year. There is another way of writing this, though I'd not prefer uh, using this. It's you'd see why, because when I do this, I have to type in manually what the name of my variable is rather than uh, writing data raw and then it giving me suggestions after I type in dollar sign. So again, it's inconvenient in my case because I have a special character for some reason because of some bug on my system. So it shows up a special character before my X variable, and my keyboard does not have that special character for me to type in. So there are because of reasons like this, I prefer using the first form rather than the second form. But if you do tend to use the second form, then you need to specify data equal to data.raw. So Both of these should essentially work the same way, and I'll run just one of these, and I'll type the summary for the linear model. So the summary statement gives a lot of results. I'll be interpreting one by one what these results are. Now it first shows up residuals. It shows me the minimum value for the residuals. It shows me the first quantile, which is essentially 25 percentile, the median, third quantile, which is 75 percentile, and the maximum value for residuals. Apart from this, it throws the estimates for my coefficients, which would be the intercept and the slope in my case. The estimate shown here is 1.581 times 10 power 3, which is essentially minus 1580 as printed here. It's the same thing. And the value of the slope that's printed is 0.807, which is again the same that we saw from the statistics. Apart from the estimate, it also throws the standard error for the estimates. So essentially, what we're looking. So think of it this way. R does not exactly estimate the value of the intercept and the slope, but there is some standard error associated with the estimates that it throws. So the actual value of the intercept and the slope would be the estimate plus or minus the standard error. Apart from that, it shows the t-value from the t-test. The professors will be talking about this a little more in class, the statistics behind the t-test, and the p-values, which essentially tells me if the variable is significant or not in predicting y. So in my case, there are significance codes associated with each of my variables here in R. You can see that 3 stars here correspond to a 1% significant level, which essentially is a 99% significant level. So when a p-value is this low, it means that the null hypothesis that the x variable does not really explain the y variable is rejected because of a low p-value. Apart from this, it also shows the residual standard error and the degrees of freedom associated with it. It shows the multiple R-squared value that you already calculated manually. If you remember over here, it's the same value if you notice. And it also shows an adjusted R-squared value, which is a corrected R-squared metric, which the professors will be talking about during the course. And apart from that, it also shows the F statistic and the p-value associated with the model. So the easiest way to remember this is if it's a simple linear regression that you're dealing with, which is y against a single x variable, the p-value for your x variable would be the same as the p-value for the model because the model has only one variable in it. Well, this is what the summary statement of the LM looks like. And again, the easier way of creating a residual plot is to first create the linear model using an LM statement and then use plot resid of the object that you used for the LM statement. By doing this, it should plot the same plot that we saw over here. So just to quickly summarize, so we talked about creating an R project and the benefits of creating an R project. And we saw how to visually analyze the relationship between variables by plotting data and also calculating the correlation coefficient and the statistics behind it. We also saw how to add a new data point to an existing data set and use the LM statement for simple linear regression and the statistics behind it. That would be all for this session. Please remember to subscribe to this channel to receive notifications when the next video is out. And thank you for joining in.